Hello. Today we'll be continuing with our previous topic, that is damped oscillators, and we will look at a few more things about damped oscillators. इसके पहले जो भी हमने डिस्कस किया, अगर उसमें आपको कुछ डाउट है तो आप इसके पीछे के जाके वीडियोस देख सकते हो. आज हम कुछ और चीज़ों के बारे में बात करेंगे जिससे हम और बेहतर damped oscillators को एनालाइज कर पाए मैथमेटिकली. सो द फर्स्ट टॉपिक दैट आई वांट टू डिस्कस टुडे, द फर्स्ट थिंग दैट आई वांट टू डिस्कस टुडे इज द एनर्जी इक्वेशन. Is the energy equation. Now, for an undamped oscillator, जब इससे पहले हमने undamped oscillator पढ़ा था, तो आपको याद होगा कि किसी भी undamped oscillator की जो energy है, it remains constant. The energy remains constant. If this is time and this is energy, the energy of an undamped oscillator is always constant. And if you remember, this energy was, I'll just call it E naught, was half k a square. Half into k into a square, which was constant throughout the motion, and the motion goes on indefinitely. Now we want to see what happens to the energy of an undamped oscillator, and for that we have a derivation, but I'm skipping the derivation. I'll just give you what is the relation. The relation is the rate of change of energy with respect to time is equal to minus r into dx by dt the whole square. Okay, this is the rate of change of energy of an damped oscillator. So first of all, you might have noticed that there is a minus sign. This minus sign tells you that the energy is decreasing. Here the energy was constant, now the energy is not going to be constant. It can't be constant. How the graph will be, we'll come to in a moment, but it won't be constant for sure. It is reducing with time, so it has to be some kind of a falling graph. First thing. Secondly, what is this rate of change of energy dependent on? The rate of change of energy, or rather this can also be called the energy dissipation, because it is losing energy, it is spending energy doing something. What is it spending its energy on? It is spending energy overcoming the opposition from the medium. It might be friction or viscosity. फ्रिक्शन और विस्कोसिटी में को ओवरकम करने में जो एनर्जी वो खर्च कर रहा है, दैट इज द एनर्जी डिसिपेशन. डी बाई डी टी इज गिवन बाय माइनस आर इंटू डी एक्स बाई डी टी स्क्वायर. दिस इज फर्स्ट ऑफ ऑल डिपेंडेंट ऑन द डैम्पिंग कोएफिशिएंट. द हायर द डैम्पिंग कोएफिशिएंट, जितना ये डैम्पिंग कोएफिशिएंट हाई होगा उतना ही आपका एनर्जी लॉस ज़्यादा होगा. जितना विस्कस मीडियम है उतना ज़्यादा एनर्जी लॉस, जितना कम विस्कस मीडियम है उतना कम एनर्जी लॉस, सो ऑन एंड सो फोर्थ. ओके, नाउ though this is a relationship which gives you the relationship of energy with respect to time, this is not giving you energy is equal to something. So that is why we'll write a second relation, that is the average energy average energy at an instant. Now you might have immediately noticed, first of all हम उसको energy नहीं बोल रहे, and we are saying this is the average energy for a particular instant, because every instant the energy is going to be changing, and the relationship here is going to be E bar. I am writing this bar on top to denote that this is the average energy, and this is not just the energy, this is the average energy. Average energy is given by half into ka squared, half into ka squared e raised to minus capital R small t by m. Now what is this half k square? इस इक्वेशन में ये जो हाफ के स्क्वायर है, what is this half k square? This half k square is nothing but E naught. And what is E naught? E naught is the energy of an undamped oscillator. That means when time t is equal to 0, the energy of a damped oscillator and the energy of an undamped oscillator will be same. इस पॉइंट पे damped और undamped की energy same होगी, पर उसके आगे undamped oscillator will continuously lose energy exponentially. It will lose its energy exponentially. So that's why this equation can also be written as, I can write this as E bar is equal to E naught. E naught is the undamped energy multiplied by a decaying factor or a reducing factor of e raised to minus RT by m. So first of all, I had the energy equation, and then I have the average energy at an instant. Now we need some more relations, and the third relation that I want to talk about is the power. What is the power? So again I will write the power dissipation, or how much energy is being lost or how much energy is being spent. What is power? Power is nothing but the rate of work done. How much work is done in a unit time, or in other words, how much energy is used, spent, released per unit time is nothing but work, is nothing but power. Now you already have energy per unit time, isn't it? We already have energy per unit time. So power dissipation P is also equal to R into dx by dt whole squared. R into dx by dt whole squared. Okay. So this is another way you can write power. Again, what is the average power dissipation? The average power dissipation will be P bar is equal to half into R A squared omega squared e raised to minus R T by M. Again, the average power being dissipated is constantly going to reduce. Okay. What do these four relations tell us? First of all, we started with the energy equation, and we also wrote down a few equations for power dissipation. See, who gives the oscillator the energy? We give it the energy. At its equilibrium position, हम consider कर सकते हैं कि उसकी energy zero है. So let us assume the energy is zero. Now I displace it. I have given it some energy. Let's say I gave it 50 joules. I gave it 50 joules, and now I let it go. See, slowly this 50 joules is reducing and coming to zero. Because it comes to zero, that's why it stops. That is why the motion stops, right? How much energy is it dissipating in 1 second? That is given by this E bar. Okay, every second it is going to dissipate some kind of energy. How much energy it dissipates is what this average energy gives you, and that is the same value that the power dissipation gives you. Okay, now I want to move on to another parameter that is very important when we talk about underdamped motion. We know that there are three kinds of motion: overdamped, critically damped, and underdamped. And if you have a doubt, you can just go back and revise what we have done previously. But hopefully you remember that overdamped motion, there was no oscillations. Critically damped, there was no oscillations. But in underdamped motion, we had oscillations. And if you remember, the oscillations look something like this. This is displacement versus time, and the oscillations look something like this. It goes on, and then slowly goes on decreasing, and finally drops to zero. Okay, finally this whole thing comes to zero. The displacement stops. Now, how much energy is being lost? There is a number that can tell you how much energy an oscillator is losing, and that particular factor is called quality factor. It is going to be a unitless number, but this number will tell you the quality, or in other words, the efficiency. If it is losing a lot of energy, that means it is less efficient. If it loses a small amount of energy, then that particular oscillator in that particular medium is more efficient. So quality factor is going to be just some kind of a number. Now, how do we define this? Quality factor is defined as 2 pi times the energy stored in an oscillator, to the dissipation, that means how much energy is being spent, dissipation of energy in one oscillation, okay. So first time we store some energy, then every oscillation it loses. How much energy is being lost in every oscillation? That is what the quality factor tells you. So basically the formula is simply, again I'm skipping the derivation, I'm just giving you the relation, that is m omega upon r. Quality factor is given by m omega upon r. This is the quality factor formula. Now, what is this again telling you? If you notice carefully, then you can see that m is the mass of the oscillator. That depends on the oscillator. Mass depends on the oscillator. Omega is the angular frequency of the oscillator, and R is the coefficient of damping of a particular medium. That means for a given oscillator and a given medium, if you fix the oscillator, let's say simple pendulum, you fix the medium water. For a given combination of an oscillator in a medium, there will be a unique value of Q. that will differ from medium to medium. If you change the medium, the value of Q should change. If you change the oscillator, the value of Q should change. So Q can help you to compare two mediums. Q is something that can help you to compare two mediums. And this is fairly easy to find. You know how to find R. You know you can measure the mass, you can find the angular frequency. Of course, how do you measure R? The best ways to use log decrement. Use log decrement and find R. Using these three terms, you get the quality factor, which tells you how quickly an oscillator loses energy. Let me give you an example. Okay, let me just give you a quick example, just so that you get a kind of idea of what this quality factor is. Let's say let's take two cases. The first case is the energy stored in an oscillator is 50 joules. The energy stored in an oscillator is 50 joules, and the energy used or energy dissipated per cycle or per oscillation, suppose it is 10 joules. What will be the quality factor? Quality factor formula is 2 pi times energy stored, that is 50, divided by energy lost per cycle. This will become 10 pi. This is the first case. Second case, suppose the energy is again 50 joules. The energy stored is still 50 joules, but now the energy used per cycle is equal to, now I'll call this 25 joules. This is 25 joules. Oh, I hope this is still visible. Okay, sorry. So this is 25 joules energy used per cycle. Now the quality factor will become again 2 pi into 50 upon 25. This will become 4 pi. So see, this value is 4 pi, this value is 10 pi. That means here it is going to oscillate for a large amount of time, because it is losing less energy. It is losing high energy. Again, if you look at the formula carefully, if your damping coefficient is very, very high, then your quality factor is very low. That means you hardly will get any oscillations. But on the other hand, if your damping coefficient were to become 0, what is the meaning of damping coefficient become 0? You place it in a medium where there is no friction, no viscosity. For example, you place it in vacuum. If you were to place this whole thing in vacuum, then what would be the quality factor? Infinity. What does infinity tell you? No energy is being lost. The energy lost per second is 0. There is no energy loss at all, and the energy remains constant throughout the motion. Okay, so these were some terms, some factors that help us to understand the damped oscillator better. Okay, so we'll stop here and we'll continue again in the next video. Thank you.